In this work, we present two large-scale datasets for federated learning on visual classification and two algorithms to alleviate the challenging problems these novel real-world federated learning datasets bring. Federated learning is a new learning paradigm that enables mobile devices to collaboratively learn a shared prediction model. In conventional data center learning, data are centralized, and models are trained by sampling randomly from the whole datasets. In contrast, federated learning moves the training of models on device. Each device learns from its local data, summarizing the change to the model as a small focused update. Model updates from multiple devices are then sent to the cloud via encrypted communication, where they are averaged with other user updates to improve the shared model. This allows learning to proceed without the data ever needing to leave the device. This is advantageous for user privacy, but brings challenges for learning due to the uneven distribution of data at the edge devices. Whilst in centralized training, data can typically be assumed to be independent and identically distributed. This assumption is unlikely to hold in federated settings. Decentralized training data on end-user devices will vary due to user-specific habits, preferences, and geographic locations. For example, in natural world classification, visual categories vary with location, so users in different locations will likely have very different training data distributions. Also, some users may take more photos than others, leading to differing amounts of data available for training at each device. Existing datasets for federated visual learning are very distinct from real-world data. Practical datasets need to derive from actual user-based data, contain a larger amount of instances, carry high-resolution images typically existing in modern mobile devices, and preferably stem from a bigger pool of visual concepts. As we see, these datasets leave much to be improved, and hence there are some goals we wish to achieve with this work. In this work, we not only provide practical datasets for federated visual classification, but we also want to provide a spectrum of datasets with varying levels of inhomogeneity across client data, which we also refer to as client non-identicalness. In the most extreme cases, we would like to see some existing algorithms to show performance degradation, and we propose some improvements to combat the harsh conditions our datasets offer. The first federated visual learning problem we're interested in is the classification of natural species. In the iNaturalist dataset, city scientists are using their mobile devices to take photos of natural images throughout the globe. They would then tag these images with the actual species information and upload them to the website, where the geographic location at which the photo is taken is also recorded. This ultimately becomes a dataset with which we can perform fine-grained visual classification and emulate federated learning. It is interesting to know that each user, while taking the photos, has their preference for geolocations and species, and thus will introduce non-identicalness across the client population. Moreover, since the different species have their respective proper habitats, the geographic distribution of species will apparently be also distinct. The raw dataset contains 5,000 species classes, and yet the distribution of photo count per class is extremely long-tailed, and as a result, 76% of the classes have less than 100 photos. We choose to first curate a dataset with balanced classes to better study the effect of client non-identicalness in isolation, and we therefore retain at most 100 photos from each of the classes with 100 photos or more. As a result, we end up with a dataset of 1,200 classes and 120,000 images. We call this dataset iNaturalist User 120K, and it has over 9,000 federated clients, more than that of any previous federated visual learning datasets. Besides this single operating point, we also wish to partition the data into federated clients in a different manner. To achieve so, we utilize geographic locations and bin the images into S2 geographic cells. S2 cells offer a covering of the Earth and are a hierarchical grid system where each cell can be subdivided into 4 smaller cells. We repeatedly break the cells into smaller ones until no cell contains more than n images, and call this dataset iNaturalist GeoN. Changing the n also changes the granularity of the clients and hence the number of clients. We use 4 different values of n, yielding 11 to 3600 federated clients. In the second Federated Visual Classification problem, we look at instance-level landmark recognition, where the images are taken from landmark locations all over the world. The raw datasets consist of over 5 million images from over 280,000 users and is, however, noisy. We extract a sanitized subset and require every landmark to be visited by at least 10 users, meanwhile requiring every user to have contributed at least 30 images that depict 5 or more landmarks. The resulting datasets, landmarks user 160K, has 160,000 images of 2,000 landmarks from 1,260 users. Unlike iNaturalist, we do not explicitly balance the classes so that we more closely approximate real-world data. The first experiment we conduct is about the effect of non-identical clients. The non-identicalness is evaluated with the Earth mover's distance of clients' class distributions with respect to the test set, and is shown on the top row. The more to the right of the charts, the more distinct the clients are and also the harsher the learning conditions are. The performance of learning is plotted in the bottom row. In CIFAR 10 and 100, we follow previous works and synthesize federated clients for learning. In the rightmost column, we use our iNaturalist Geo and iNaturalist user datasets. The interesting phenomenon is that despite the vastly dissimilar input and task these datasets have, they exhibit quite similar behavior when plotting the classification performance on the y-axis against non-identicalness metrics on the x-axis. Moreover, the red curves all show significant improvement over the blue ones because in these cases, the server adopts momentum in its optimizer. When more clients are involved in federated learning per communication round, there is also an apparent performance increase. In pragmatic federated learning, previous algorithms also suffer from unequal client data pool sizes. That is to say, when one large client holds much more data than others do, it not only takes more time for the said client to finish local optimization, but the updated model has substantially drifted weights so as to temper the aggregated model. We propose FedVC, a scheme that builds on top of the federated averaging algorithm, and it views these large clients as multiple smaller clients with the same underlying data. In essence, instead of performing more optimizations on the large clients, causing a straggler effect in communication rounds, we perform equal steps on all clients, but selecting larger clients more often. Regardless of the client sizes, they could also suffer from data bias problems, where the local data distribution is far from the target distribution on which you wish the model to perform well ultimately. We adopt importance reweighting and propose FedIR to further reweight the local loss objectives so that it aligns with the global objective better. FedIR proves to consistently improve classification accuracy in landmarks user datasets. The two algorithms, FedVC and FedIR, can be applied together since they deal with tangential aspects of real-world federated visual learning. In conclusion, we have shown that large-scale visual classifiers can be trained via federated learning and have proposed modifications to mitigate the effects of non-identicalness and imbalance in real-world data. We introduced 2 new datasets and benchmark, which we hope will inspire further research in this area. Thank you, and please find our datasets online at the URL or search Federated Vision Datasets.